What's up, team? This is Ro, your best friend at JMSB. So here I was asked a question for COMM 215, Introduction to Business Statistics. Let's have a look. Problem number 3. Given below are 4 observations collected in a regression study on 2 variables, x the independent variable and y the dependent variable. If we have a look at required A, it tells us to develop the least squares estimated regression equation. Now this is very typical of a simple regression question. The very first thing they often ask you to do is to calculate the regression slope and intercept coefficients. When you are doing that, sometimes what happens is that they offer you the required or needed summations. So the totals of x and y and so on are simply given in the problem. Other times you're offered a sample, which happens to be the case here. We have a sample of 4 observations, and we're not given the totals, so the first thing that we're going to do is find them. In order to do that, in the question itself, I'd encourage you to create 3 extra columns. One for xy, one for x squared, and one for y squared. So in the xy column, we're simply going to be multiplying the paired observations. So 2 times 4 is 8, 6 times 7 is 42, 9 times 8 is 72, and 9 times 9 is 81. In the column over, we're going to be squaring the values of x. So 2 squared, 6 squared, 9 squared, and so on. And then finally, we've created a column for y squared, and here we're obviously squaring the y values. And now once you've done this, you've created these 3 extra columns and filled them up with the values. Now you're hoping to find the totals. The reason why you need these summations is simply because these are the values that are going to be plugged in into the simple regression equations that are offered on your formula sheet. So you need things like sum of x, sum of y, sum of xy, sum of x squared, and sum of y squared. And so as I said earlier, sometimes these summations are already offered. In the case when they're not, the first thing you gotta do is simply find them. And now that we've done that, we're gonna begin calculating the coefficients for our regression line. Try to remember that you have to always calculate the value for the slope coefficient b1 prior to being able to calculate the value for the intercept, which is b0. And that's simply because you need b1 in order to find b0. So you always find the slope first, then you find the intercept. Another tip that I want to offer is to remember to always calculate the numerator and the denominator of your slope coefficient individually. So it's a pretty chill idea to calculate the top part of this equation, figure out what the bottom part is, and then only to divide the 2. And the reason for that is because this bottom piece, sum of x squared minus sum of x all squared over n, or SSXX, is used in many other equations in simple regression. So rather than calculating this piece over and over again, you'd rather calculate it once and sort of remember what the value is. And now it's really just a matter of plugging in the totals that you've found into the equation for B1 that is offered and to figure out what B1 is. Try to remember that the numerator for B1 is called SSXY. So the numerator is the sum of xy minus the sum of x times the sum of y over n. And if I were to plug in the totals that we calculated earlier, I can obtain the answer for SSXY, which happens to be 21. The denominator is called SSXX. It's the variance of the x value, or the x variable rather. So sum of x squared minus sum of x all squared divided by n. And once again, it's really just a matter of plugging in these creatures where they belong in the equation that is offered. It looks scarier than it is, but all you're doing is just plugging in totals that you have found. So if I substitute 202 for sum of x squared, for sum of x, I'm going to plug in 26. We're going to square that, divided by n, you should be getting an answer of 33. And once you've gotten the numerator and the denominator, you simply have to divide the 2 to obtain your answer for B1. And so if you work that out, I'm hoping you get an answer of 0.63 repeated. Once you've found B1, now you can plug that into the equation for B0. The way that we find B0 is by taking the difference between the average of the y's and B1 times the average of the x's. So y bar and x bar simply are the averages of the respective variables. So you add up all the y values and you simply divide by how many there are. And you can do the same to get the average of the x's. And so if you evaluate that, you should be getting an answer of 2.863 repeated for your intercept coefficient. Once we've calculated the slope and the intercept, we can now express our regression line. So our regression line comes in the format of a straight line. It's y hat equals b0 plus b1 times x, where b0 is your intercept and b1 is your slope. So there we have it. That's how we would answer required A. Now let's have a look at required B. So here it says, obtain a numerical value to measure how well the regression line fits the data. In this case, the value that you're looking to calculate is the standard error of the residual. The way that we calculate SE is first by calculating SSE. Now in your equation list, if I'm not mistaken, the only equation they're going to offer you for SSE is this equation. And the truth is, if they offer you this equation, they'll more often than not tell you what the answer to this term is. So more often than not, SSE is likely to be given simply because this is a very tedious calculation to perform. The alternative is to calculate SSE this way, but this expression is perhaps not offered on the equation list this semester, so I'd encourage you guys to double check that, and if they don't offer you this equation, unfortunately you got to memorize it. So this is how you find the sum of squared error. Once again, all you're doing is you're plugging in the totals that you have found and the values for B0 and B1 that we have computed in part A. And so if we plug those values in, the answer that we get for SSE happens to also be 0.6363 repeated. Now it's simply a coincidence that SSE happens to be the same answer as the slope. That doesn't always have to be the case. Once we've found SSE, we can now find S, the standard error of the residual. It is simply the square root of SSE divided by n minus k minus 1. What's also pretty chill to remember is that when we divide SSE by n minus k minus 1, that concept tells us MSE. So what's inside of the square root is called MSE, the mean squared error. So once we've found SSE, we know that n is the number of observations, which is 4, k is the number of independent variables, which in simple regression is always 1. We're able to divide the two to calculate S. And we should be getting an answer of 0.564 if we round to the third decimal. Now what's more important is to understand what this value is telling you. Why is it that S is a measure of how well the regression line is fitting your data set? Well, simply because the value for S tells you precisely that. It tells you on average how far are the actual values from what the line is going to predict. So if you had to interpret the answer, you would say something like that. You'd say that the standard error of the residual, or the error term, tells us that on average, the actual values plot 0.564 away from what the regression line would predict. So I apologize for this little typo here. It should read of rather than or. So I hope that helps. That's the answer to part B. Let's move on to part C. Here it says, at a 5% level of significance, perform a t-test and determine whether or not the slope is significantly different from 0. So at this point, we got to perform the steps for a hypothesis test. The very first step of any hypothesis test is simply to express the null and the alternate hypotheses. And in this example, we're being told that we want to figure out if the slope is different from 0. Since it says that, you should be aware of the fact that you'll be conducting a two-tailed test rather than a one-tailed test. Had I said test if there's a positive linear relationship or a negative linear relationship, now that would be a one-sided test. But here we're simply detecting whether x and y are linearly related or not, because we're testing if the slope differs from 0 or not. So the way that we express the hypotheses would be as follows. In HO, I would say that B1, the population slope coefficient, equals 0. And in HA, I am testing if the slope is in fact different from 0. Whenever we conclude HO, it means that x and y are not linearly related. In contrast, when we conclude HA, or we reject HO, this would imply that a linear relationship does exist. And that's simply because when the slope is different from 0, it would mean that x and y have either a positive or a negative relationship. In step 2, what we're hoping to do is to calculate the test stat, or the observed value. Now, whenever we're doing a hypothesis test for the slope coefficient of a regression line, it's always a t-test that is being conducted. And so the observed value is a t-stat. To calculate your t-stat, you need to first begin by finding SB1. The way that we find SB1 is by dividing S by the square root of SSXX. Once we've found SB1, we can now find our t observed, which is simply B1 minus big B1 divided by SB1. Now what's pretty chill is that we've already found S, and we've already found SSXX. This guy right here, SSXX, is simply the denominator for the equation for the slope. So we already know what these two values are. We've evaluated them previously. We can plug them in and find SB1. So for SB1, we should be getting an answer of 0.0982. Once we've found SB1, we can find our t observed. In the equation for t observed, we need to know B1, which was our sample slope coefficient. We found that in part A. We found SB1 by applying this equation. And the value for big B1 is whatever is in your hypotheses. In this course, this guy is always going to be a 0. So it kind of simplifies the equation. Big B1 in this course is always going to be a 0, simply because you have a 0 in your null and alternate hypotheses. And so if you divide your sample slope by its standard deviation, you'll be able to come up with your t observed. So I'm hoping we get an answer of 6.48 for t observed. The third step is to either obtain a critical value if we're using the classical approach, or a p-value if you're using the p-value approach. Either way, performing this step does not require the use of a calculator. It's really your ability to work with the probability tables that are offered, specifically the t-table in this case. So here's an excerpt from the t-table. Let's imagine we wanted to use the classical approach. Under the classical approach, we have to obtain the value for t critical. The way that we do that is we simply work our way down to the appropriate degrees of freedom, which in the case of simple regression is always n minus 2. So in our example, n was 4. 4 minus 2 would mean that there are 2 degrees of freedom. In the very first row of your table, you want to go look for your value for alpha if you're conducting a one-tailed test, or alpha over 2 when you're conducting a two-tailed test. In this case, we're doing a two-tailed test, and since alpha is 5%, we're going to go look for half of alpha in the very first row of our table, so 0.025. And now it's really a matter of connecting these two, and then to obtain the critical value from the inside of the table. So 4.303 would be the critical value for t. So notice that this does not require the use of a calculator. It's really your ability to look up n minus 2 degrees of freedom in the first column, alpha over 2 in the first row, and then to connect them in order to find your t critical. And So to help you visualize the classical approach, under the classical approach, what is happening is we're coming up with the value for t critical, and t critical is essentially separating the rejection and acceptance regions for your test. So in our example, the critical value for t is 4.303 and negative 4.303 because it's a two-tailed test. And again, as I mentioned, this critical value separates the HO region from the HA region. Under the classical approach, you simply compare t critical and t observed to determine whether HO or HA is the valid hypothesis. So in our example, we can see that t observed is 6.48, and because 6.48 is a larger value than this critical value, we're in the HA region. So we would be rejecting HO in favor of HA. The alternative is to use the p-value approach. Under the p-value approach, what you're essentially doing is you're comparing the p-value, or the observed level of significance, to alpha, the assumed level of significance. So we compare the p-value to alpha, and that's what helps you decide which statement is correct. Whenever the p-value is smaller than alpha, you are rejecting HO. In contrast, when the p-value is higher than alpha, you do not reject HO. To find the p-value, you do not need a calculator. You just need to know how the t-table works. On the t-table, you're first going to settle at the correct degrees of freedom. So in our example, it would be n minus 2, 4 minus 2, so I'd be at 2 degrees of freedom. The idea now is to scan this row until you find a number that is bigger than your test stat. So our test stat is 6.48, and I finally found a number that is bigger than my test stat of 6.48. So I stay on 2 degrees of freedom, I scan this row until I find a number that is bigger than my test stat. So that would be right here. And then once you've done that, you just go scan the first row of the table to get the p-value. So had this been a one-tailed test, the p-value would be between 0.025 and 0.01. But because it's a two-tailed test, you must multiply each of these numbers, or areas rather, by 2. So in our example, the p-value is simply going to be between 0.05 and 0.02. And try to understand that the p-value is simply the area that is in the tail relative to your test statistic. So our test statistic was 6.48. The p-value is the area that is in the tail relative to that value. However, whenever it's a two-tailed test, because there are 2 rejection zones, you multiply this area by 2, precisely like we've done. We've multiplied 0.01 by 2 to get 0.02, and 0.025 by 2 to get 0.05. So once we've done that, we can either use the classical approach or the p-value approach to make a decision. And so you could say things like, since the test stat 6.48 is bigger than the critical value of 4.303, or because the p-value is smaller than alpha 0.05, we reject HO. In your conclusion, it's not a bad idea to repeat the level of significance. So you'd want to say things like, we reject HO at a 5% level of significance. And you could say things like, the data provides sufficient evidence to support the claim that there is a linear relationship between X and Y. So once again, whenever you are rejecting HO, it means that X and Y are in fact linearly related. So I hope that helps. Let's have a look at the next required. Here it says, calculate the coefficient of determination and interpret its meaning. So the coefficient of determination is simply the answer to r squared. In order to calculate r squared, the first thing we're going to have to do is to calculate SST, the sum of squared total, or the variance of y. The way that you do that is by taking the sum of y squared and then minusing the sum of y all squared over n. So this equation should remind you of the equation for SSXX. You simply switch all the x's to y's. The reason I'm saying that is because it's probably not offered on your formula sheet, but you don't really have to memorize it. You're offered the one with the x's. If you want to find the sum of squared y's, then just replace the x's with y's instead. And so since we found all these totals, we can plug in the values and calculate SST. You should be getting an answer of 14. And so once you've found SST, you can calculate R squared. R squared is either SSR over SST or 1 minus SSE over SST. The second way of calculating R squared is not offered on the formula sheet, but I'd strongly recommend that you remember it. And that's because it saves you a lot of time. Oftentimes you know what SSE is, so you can find R squared right away without necessarily computing SSR first. So in our example, we've found SSE, we just found SST, we can calculate R squared. We get an answer of 0.954 repeated. Now what is more important for us is to know how to interpret R squared. R squared is a concept that always shows up on the final exam, and what it's essentially telling you is what is the percentage of the total variation in Y that is explained by variations in X. In other words, how good is your choice of X to predict Y? So you could say things like the coefficient of determination tells you that about 95.45% of the total variation in the dependent variable Y is explained by variations in X. And obviously the balance is the percentage that is not explained. It is explained by other factors that are not included in your model. So I hope this explanation helps. I hope you guys keep studying, and whenever you're stuck, feel free to post your questions in the group. If you think it's something that could help you, it could definitely also help your friends. So be a good friend and make sure that you let them know about it. Good luck for your courses, guys. Bro, out.